Okay, in this class, we are going to be looking at systems that have an input. All right, so let's call this input x of t. And in general, we're going to assume LTI systems, although there will be some cases where we look at possibly nonlinear time, not time invariant systems. But for now, we're going to concentrate on LTI systems, namely those that can be described with an ordinary differential equation. All right, so you put in an input and you get out an output is the way we're thinking of this. All right, so it's an input-output relationship. And ultimately, we've talked about if you use a special input, if you put x of t to be an impulse, put an impulse into this LTI system, what you get out is h of t, all right? And so we could then take a look at the Laplace transform of h of t and call that h of s. And under special conditions, namely, we consider the system being initially at rest, there's no energy stored in the system. Under that condition, this is called the transfer function. Okay? And so part of the reason we want zero initial conditions is that when you looked at solving a differential equation, we'll write one down here in a second, but when we looked at solving that in your ODE course, you had a homogeneous response plus a particular response. Okay, so typically, if there's no energy stored in the system, that homogeneous response, which was used to hit certain initial conditions, typically you can neglect that. That would be zero. All right, and your total solution would be what's due to the convolution part that comes from linear system theory. All right, so the reason that's useful for us is now we can look at this and we can call this h of s, where h of s is this transfer function idea that we just talked about. And I put in x of t and get out y of t. Now in a previous video, I told you you shouldn't mix domains here, but this is not really mixing it because this is just a label. We are saying this is the linear time invariant system described by h of s, and we're going to put in time varying signals x of t and look at the output y of t. All right, and what we know from the convolution property, that we didn't talk about the details of why this is true, but for this class, you're just looking at mainly results so we can apply these results to get some practical things done with the control system. So the result for convolution is that y of s is equal to h of s multiplied by x of s. All right, so that's what we're after, and we're going to go into a little more detail about why that would be the case. All right, so what I want to do next is write down a differential equation. So I'm going to make it sort of in general, but I'm only going to go up to third order. We could do whatever order you wanted here, but let's take a look at y triple dot for the third derivative plus some constant. I'm just going to make up numbers. We could put letters to represent, symbols to represent these coefficients, but let's make it simple. So 2y double dot plus 6y dot plus 3y is equal to, and we could have derivatives of the input showing up in this equation as well. So maybe, let's say 7x double dot plus 3x dot minus 2x. Okay, so when I say this, like y triple dot, I really mean that it's a function of time, but it just takes too long to write that explicitly. Okay, so I'm not going to do that. All right, so the next thing I want to do here is I want to take the Laplace transform of this whole entire equation. All right, and remember, we assume that the system was at rest, so all the initial conditions are zero. which makes it a lot easier to apply the derivative property of Laplace transforms. So taking the Laplace transform of both sides. All right, when I see a derivative, remember I get powers of s that show up, all right? So the third derivative means I get s cubed y of s. Notice also, lowercase y, I'm talking about a time signal. When I take the transform, I use an uppercase y to denote the transform. I drop the dependency on the explicit notation on t, so I use a lowercase y for y of t and an uppercase y for y of s. All right, so that's our shortcut notation that makes it easier to write things down. All right, so keep that in mind. Okay, so back to where we were. Third derivative, I get s cubed, and then I won't, multiply by cap y. Second derivative, I get 2s squared cap y plus 6sy. You catch what I'm doing? Every derivative gets an s. All right, there's not a derivative on this term, so this would be plus 3 cap y. All right, so that takes care of the left-hand side of the equation. And we can write down the right-hand side by just 7s squared x plus 3sx minus 2x. So I'm just taking the Laplace transform of each component. Anytime I see a derivative, I put an s. All right, so it's a second derivative, I get s squared. First derivative, I get s. There's not a derivative on this term, no s. All right, so you get the idea. At this point, I can factor out the y of s. All right, when I do that, I get s cubed plus 2s squared plus 6s plus 3 equal to, all right, now I'm going to factor out x of s, and I would have 7s squared plus 3s minus 2. All right, so from there, I'm using the idea that y of s is equal to h of s times x of s. Okay, so if I solve for y, I would have y of s is equal to 7s squared plus 3s minus 2 divided by s cubed plus 2s squared plus 6s plus 3. So I'm just dividing through by this quantity times x of s. Okay? So I put on my pattern recognizer and I tell myself, so this part right in here, this part must be h of s. Okay, and that's exactly right. Okay, so this is h of s, the transfer function. So in summary, we start with a system. All right, we're going to write in Module 4, we're going to start looking at practical systems and how to write the differential equations. All right, so these would be differential equations, but we want to look at them from an input-output point of view. All right, so if I put in a delta function, I get out h of t, the impulse response. If I take the Laplace transform of the impulse response, I get capital H of s, which is also the transfer function. Okay, so then I took an approach where I used properties of Laplace transforms. So I'm just applying the derivative property over and over. And I solved for the transfer function of this example system that I came up with. All right, so it's pretty straightforward to generalize that. So if I gave you any transfer function, any ODE, you could write down the transfer function almost by inspection. Okay, let's do that real quick. So let's say if I had y double dot plus 6y dot plus 3y is equal to 2x. All right, what is h of s? All right, this is the ODE. What is h of s? Okay, well, I know that on the bottom here, it's the coefficients from the Laplace transform of the left-hand side of the equation. So you see when I see the y double dot, I write down the s squared down here, plus 6s for the y dot, plus 3. And x doesn't have any derivatives, so that would just be a 2. All right, so by inspection, I quickly wrote down the transfer function of this system. Okay, so I want you to be able to do that. And from there, we can talk about what the solutions would look like given different types of inputs.